In the last class, if you remember, we had tried to find out that how can we actually come up with a better kind of classification of lookups, like how can we look up faster our IP addresses that we are getting, so that the search time becomes smaller. Okay, so for that, first we checked out at naive algorithms. Okay, so in naive algorithms, what we were doing, that we just have basically it is a linear search of prefixes. So we just have an array where the prefixes are stored, and then the search will iterate through each prefix and compare it with the destination address. Okay, so that is of course going to be time consuming. And after this naive algorithms, we thought that okay, let us store the prefixes in such a way so that the search time becomes lower. Okay, so that is why binary tries was proposed, where we had done something like this. That means you have the set of prefixes with you, and you store it as a binary try. Okay, so with this, whenever you are traversing the try, you will find out that for your prefix, what is the best matching prefix, and store it accordingly. Okay, so this is how your binary try works. Now, with the help of this binary try, we could see that insertion and deletion also became quite easier. Okay, so we had done up till this much, that is what is the worst case search complexity of binary tries for both insertion and deletion, and what's the memory consumption. So we had done up to binary tries in the last class. Today we are going to see some enhancements over this binary try. Okay, and what is that enhancement? That enhancement is known as the path compressed tries. Okay, so what is this path compression that we are talking about? So if you see our yes, this is the binary try that we had um, seen earlier. So here earlier it was given as P1, P2, P3. Now it is given as A, B, C, D, E, F, G, H, like that. Okay, so 0 star is the prefix. So there is 0 star. So you have A here, and then B 0, 1, 0, 0 star. So 0, 1, 0, 0, 0, and here you get B here. Okay, so this is our simple binary try that we were looking at. Now you can see that here there are many nodes which are basically having no prefixes, but they form a part of a bigger or a bigger length prefix, like this B. Okay, so B is like 0, 1, 0, 0 star. So that is why we are going like this. But these two nodes are actually not having any particular information regarding any prefix. Okay, so this is the concept of path compression. So here lies the concept of path compression. That is, we try to compress these, not see, these are not very important nodes. They are just forming a path to a particular prefix. Okay, so we try to compress these nodes, and we want to have like a smaller try as much as possible, so that your traversal becomes lesser and your entire search time also lowers down. Okay, so this generally would be helpful for those kind of tries where it is like sparsely populated. Okay, so suppose you have some prefix which is like 0, 1, and then some 4 zeros and or 5 zeros, or even something like this, that is 1110 is here as H. So you can have like 111, then 4 zeros and then a star, like that. So in those cases, your path is becoming longer and longer here as a binary try, and it is also taking up a lot of time to traverse and a lot of space also. Okay, so this is the basic reason why we are going for a path compressed tree. sorry, try. Now, this path compressed trie will have only little benefit when the number of prefixes increases and the trie gets denser. That is quite obvious, right? If the trie gets denser, that means you have more and more prefixes in it, and therefore you will not have many nodes which are just simply lying down as a path to a particular node. Okay, so that is the reason that in those cases path compression will not be helpful. It will only be helpful in cases when you have a sparse trie. Okay, so we need to this search through this path compressed trie may need to do many memory accesses. Now we will see why and how a path. First of all, let's see how a path compression trie could be made. So let us look at this. We are having a binary trie here. This is the root node. I hope that my mouse is visible to all of you. This is the root node. Left child is A, right child is D, and the corresponding bits that represent these or that represent the prefix is 0 and 1. Okay, because here in the prefix A is 0 star and D is 1 star. All right. Now, what are we basically doing here? We are basically checking. So suppose you have some prefix, some IP address that you have got. Okay, so essentially when you are looking at this binary trie and you are checking that okay, 0 means let's get to the left side where we have the prefix A star, and if the first bit is 1, then you go to the right side and see that okay, whether it matches with D star or not. Of course it does, and then you go further that whether there is any further match or not. Okay, so basically here what you are doing, you are checking the first bit of your IP address that you are trying to get a match from this binary trie. Okay, so what we can do, this is simply a root node, it is of no use for us as of now. Okay, so what we can do in the path compressed tree, see, we are putting the root node here. What we are doing here, these outside these root nodes, the numbers that are there that represent that which bit of the IP address you need to check. Okay, so here you will check the first bit. Okay, now 0 and 1 as usual, 0 for A as the prefix and 1 for D as the prefix. Okay, now let's get to again to the binary trie. Okay, so for this same binary trie, I'm showing you the path compressed trie. Okay, now this A does not have any left child. Here in the binary binary trie, the A does not have any left child, it has a right child, and from there you get a long this step for B. That means 1 0 0 0, then B, and then 1 1 to C. Okay, so if you are looking at B, you can see that these are two steps which are like not useful for you. Okay, these are like they do not represent any prefix. Okay, so what you can do, you can compress these two. Okay, so if you compress these two and look at C, so that means what is the number, I mean which bit are you actually going to check after coming to A, so that you can make a decision that whether you should go to the left side or whether you should go to the right side. Okay, because in the right child you have C, in the left child you have B. Here what we are doing, you go to this A, then you have compressed all of that was there here in the binary trie. Okay, you have compressed it. Now 2 bits have been compressed. For B, you get it as a left child of A. For C, you get it as a right child of A. Now when you come to this point, you have to check the third bit of your prefix that you are getting. So suppose this is the IP address that you are trying to check, or this is the just the prefix that you want to check. So here out of this you have to check the third bit when you come to this point. So that is why it is given as 3, because there are 2 steps that have been compressed here. Okay, so you check the third bit and then see that okay, whether which kind of, I mean, which prefix does it match now. Okay, so if the third bit is like 0, so you go to B. If the third bit is 1, so you go to C and then say that okay, B C, if it is 0, then you say that B is the best match. If it is 1, then you say that C is the best match. Okay, so similarly when you go to D here, so see here again, E is having like, this is one node which is like not useful for us. Okay, but here what's the case, that all the nodes are like having 2 children. Okay, and you cannot actually compress it, all of it here as such. Okay, because all the bits are, you know, 0 1 0 1 0 1, all of this are here. There is no child which is like a single child, and I mean no node which is having a single child, and that node also is not a prefix. So no unused node is here. Okay, in this case, sorry, in this right child of D. So what do? We check at D. Okay, so when you do this, when you check at D, you are basically, see again, go back to the binary try. You're coming to this part. Okay, now at D you have to make 2 decisions. You go to left child or you go to the right child. Okay, so what is the bit number that you have to check at this point? You have to check the second bit, because this was the first one, 0 star or 1 star, and then you check the second bit, and in the second bit only you will decide that okay, whether it is like 0. If it is 0, then you go towards this one saying that E is the best match, and otherwise you go to the right child saying that okay, after this we will get to see that okay, what is the further match for this. Okay, that is why at D you have 2 here, where you are basically saying that now you have to check the second bit of the address that you are trying to match. So if this is the address, then, and if it is this is not exactly the address in this case, like if there is some address like this which starts with 1, so you got to the right child, and then at this point you have to check the second bit and then make a decision, that is whether you will move to the left side or you will move to the right hand side of this tribe. Okay, now when you get to the right hand side, see for this one it is pretty simple. You got to the left side, and if there is 0 in that second bit, then you obviously go to E and say that okay, E is my best matching prefix, or BMP. Okay, but if 1 is the second bit, so then you have to again check another bit, right? So what is that? So you have already checked the second bit, got to this point, there's no prefix here, so you check the third bit here. Okay, so third bit you check again, you get to 2 children are there, so 0 and 1. Now you check the fourth bit here, and then you are finally getting to the corresponding prefixes, okay, which are given as child nodes here. So these are leaf nodes for this particular set of tribe here. Now why is this helpful for you? Okay, imagine this example that I have given, that is 0 1 0 1 1 0. Okay, now I want to find the best matching prefix. This is the try that is given to me. Okay, so what does this try say? At this point, when you start checking, it says that you check the first bit. So I'm checking the first bit here. Now this is 0. So if the first bit is 0, I go to the left hand side, to the left child. So I go to the left child, and now I get to A. So as of now, what is my best matching prefix? A star. So the A is, A, which is 0 star. Okay, so first my best matching prefix as of now is A. Now, what is the next value here? So this is 1, but I am not supposed to check 1 at this point. I am supposed to check 3 at this point, right? Bit number 3. So I skip 1 and I go and check 0 here. Okay, 0 here. So that is the left child I'm checking. Now I'm checking B. Okay, so with B, what was the thing for B? It is like 0 1 0 and then 0 0 star, which does not match this one. Okay, so what is my best matching prefix for this guy? It is the previous last best matching prefix that I've got while traversing. That is the A star. Sorry, A here, that is 0 star. Okay, so this is my path compressed trie. So what I'm essentially doing, I'm essentially reducing the steps or the number of children or number of nodes in a particular trie. So your traversal time is reduced. Your memory that is taken to store the trie, that is also reduced. And by having these values, that is 1 2 and 3, which are basically telling that which bit you need to check in your address that you are trying to find the best match prefix for, with that what you are doing is that you are also reducing the checking time. Like instead of checking all the for all the bits that, like, you know, 0, this first bit is 0, let me check whether it matches or not. Second bit is 0 1, let me check whether it matches or not. Instead of doing that, you're skipping through bits and then checking that, okay, first bit does it match? Yes. Third bit does it match? Yes. Fourth bit does it match? No, it does not match. So let's go to the last best match prefix. Okay, so this is the concept of path compressed tries. Okay, so what I will do is I do have a paper, original paper that was actually talking about this path compressed trie. It's quite an old paper. So I will share that paper with all of you. Okay, so that you can actually go through this one. And even, you know, Methi and Ramasamy also have this particular, you know, concept with them, so you can also see in that book also. Okay, so this is the concept of path compressed tries. Now let us take a look at the next types of, you know, IP lookup algorithms. Okay, so there are so path compression is also one way of looking at, you know, or trying to find out the or trying to do an IP lookup in an efficient way. Okay. Now some other new IP lookup algorithms have also been proposed. Now they are basically categorized into two ways. One is that you search on values, and another is that you search on length. Okay. So let us first understand what are search on values approaches and what are search on length approaches. Okay. So search on value approaches is considered to be the simplest method. So what it does, that it simply goes through all the entries, comparing the prefix with the corresponding bits of a given address, like, you know, what we were doing in our binary trie and all that. Okay, so you just see all the entries of the prefixes and correspondingly you check the bits in a given address. It was also being done in your naive algorithm. Okay, so you then find out that, okay, which one suits the best. And as of now, this is the best matching prefix. Then again, you keep going, keep checking that, okay, do we have a further better match than this? Like that, you can keep continuing till the number of prefixes are there in your memory, and then you find out that, you know, what is the best matching prefix. Okay, so always the last remembered prefix will be the last remembered best match prefix will be your answer. Okay, so if you are currently not getting any best match, what is the last remembered best match prefix? That will be your actual best match prefix for the address that you are basically looking up for. Now here the such complexity is O of n, and it is It is actually a very simple approach to n being the number of prefixes, of course. Now, this search on values approaches seems to be a very simple method for implementation, but like for understanding, it is very easy. For implementation, also, it seems to be very easy, but it does take a lot of time and it is not that scalable. Okay, so that is the issue with search on values approaches. And then we have another one which is known as the search on length approaches. Okay, so what does this mean? This kind of search technique bases the search on the length dimension and then uses linear or binary search on it. Okay, so what is being basically done here, that you just check that what is the length of the prefix. Okay, and then accordingly you just keep checking that okay, this is the particular length. Now let me just try to find out that with this length what is going to be my best prefix or best match prefix, by just finding out that okay, with this length, let me check with this bit, again let me check with another bit, like similar to what we were doing in case of the path compressed rise. Okay, so this is my search on length approaches. Now another set of techniques which have been proposed to efficiently look up algorithms. So these are, first one is prefix transformation. Okay, so what is it? That is instead of simply having like 0 star 1 star and then looking at okay fine, maybe this will match, again 1 star, maybe this will match, this is the best match prefix, but then there can be many other bits later on which are probably not a best match prefix. Okay, and if your matching is not correct, what will be the problem later on, that when you are, suppose you just try to have every IP address that you are getting, you are matching it to 0 star, whatever is starting with 0, and what will happen, that so this is basically going to determine the path, right? So if you are doing this, like everything you are matching to 0 star, which is starting with 0, bit 1 bit, first bit as 0, what will happen, it will send through a particular port. Okay, outgoing port, it will send that packet through a particular outgoing port. Now that might result in further, in the routing, it will create problems, because later on, when once you send every packet through one particular outgoing port, one, you are congesting that link, that is of course you are doing, but what is the biggest thing that you are doing is that if you are routing through the same thing, same outgoing port, without even checking for the best match, you are basically um, not giving that particular packet its best path to reach to the particular destination. Okay, so essentially at the end, at the user's end, basically the destination user's end, the packets are going to be received either with a lot of delay, or they will probably get dropped in between because of their time to live has been finished, or time to live has reached, or they are just waiting for some congestion, because of some congestion that has happened um, in the link in between. Okay, so these will be the issues if you do not find a best matching prefix for a particular IP address. Okay, now what prefix expansion does here? Okay, prefix expansion basically is a technique that helps to expand the prefix into equivalent set of prefixes of longer lengths. Okay, so this will basically give you that okay, I am producing prefixes of longer length, so that I will find out that which is like the best matching prefix for my lookup algorithm. So everything which looks like okay, first bit is 0, let's get to 0 star, that will not happen. Okay, it will always work like you have, like either you have to check the second bit again, then you have to check the third bit. Now instead of not checking and not getting a best match prefix, you simply just put the values, get the prefixes in the nodes, and then say that okay, this one is the best match prefix. Let us find out that what is the corresponding outgoing port for that. Okay, so this is what I'm talking about, that the forwarding information is specified with prefixes that represent ranges of addresses. Okay, now one of the most common prefix transformation techniques is prefix expansion. So you have been given, suppose, all of the 0 star 1 star like that. Now you try to transform these prefixes by simply expanding them into like 2-bit prefixes, then 3-bit prefixes or something, depending upon what is the range of addresses that you are basically looking for and basically trying to get a match for. Okay, so let me show you how it works. Oh, have I not given here? Yeah, this is what I've given here. Let us look at this. So before this, let me just give you an overview of what it is known as. This is known as disjoint prefixes. Okay, so basically prefixes can overlap with each other. Okay, 0 0 star and 0 star, they both will overlap with each other. Okay, so similarly like 1 star and 1 1 star, they do overlap with each other. Okay, so we are trying to use a concept where we transform a given set of prefixes into a set of disjoint prefixes. Okay, so that one prefix does not overlap with another. Okay, we will see how that happens. And what is the last point here? That is, a trie used to represent disjoint prefixes will have prefixes at the leaf nodes and not at the internal nodes. Okay, so let's see how these features of disjoint prefixes are put here. So you remember the binary trie. This is the same set of prefixes that has been used here. Okay, so what was the binary trie that looked like? So we had like 0 star. So A was here. Okay, in the binary trie, if you remember, A was here and then there was no left child. We had a right child, and from there you would go like 0 1, then 0 0 0 star means B here. These two internal nodes did not have any right child. Whereas this one like 1 1 star, so it comes out as C. So this was the how the left side of this binary trie used to look like. Okay, when you were simply using binary trie. What we are now planning to use, we are looking for the best match prefix with the help of a disjoint prefix binary trie. So basically, we want to have no internal nodes. We are pushing all the internal nodes to their leaf nodes. Okay, and basically what we are doing here, so let us look at this. A means 0 star. We do not want to have any overlaps, right? That's what was our motto or objective. So A is 0 star. Now if it is in the second bit given as 1, then it goes to this side, and here you have some more clarification, like again, if the third bit is 1, then you go to C, and that is the prefix. Okay. But what if your second bit is 0? Instead of 1, what if your second bit is 0? So in the prefixes given here in your suppose this is the prefixes that you already have in your forwarding table, and second bit 0, that option is not here at all. That prefix is not there at all. So what does it overlap with? Okay, so if you actually check in a binary trie, if you just had a binary trie like this, you would say that okay, A, that is 0 star, is my best matching prefix. Okay, but how we are now, we do not want any overlaps, right? So how we are trying to overcome that A can have many changes depending upon, or many variations depending upon which bit we are looking at after the first bit, right? So if we look at the second bit, we will have this as 0. That is, if we look at the second bit, it will look as 0 0 star, which also overlaps with 0 star. Okay, but that 0 0 star is not already present in the set of prefixes with you. So how do you represent it? You simply write it as one variation of your prefix A. So you write it down as A1, which is equivalent to 0 0 star here. Okay. Now when you check the second bit, if it is 1, then you get to this child, right child here. Now let us check what happens if you have when you check the third bit. If the third bit is 1, you will go to the right child of this node and you have a prefix already in your table, that is 0 1 1 star, which is C, and it matches. If that is the case, then it matches and you get your best matching prefix here. Good. Now if your third bit is 0, then what you are going to do? So if your third bit is 0, you get here. Okay. Now we will have to check the fourth bit. Okay. Now fourth bit can be 0 or it can be 1. If it is 0, then we already have some idea here that, okay, if it is 0, then also there is no, nothing here in this node, no prefixes here. And you again check the fifth bit and then find if it is 0, it goes to B, according to our normal binary try that we had earlier. Okay. Now what if you come at this point? That means after checking the third bit, you are here. Now you are trying to check the fourth bit. Okay. What if your fourth bit is 1? Okay. But there is no prefix here. In the binary try, look at the binary try. Okay. Let me get to the binary try. This is the binary try. Okay. These two nodes, they do not have, these two internal nodes, they do not have any right children. So when you are coming from like here, 0 1 0, and when you check the fourth bit, if it is 1, there is no option for this one because you do not have that prefix here. Similarly, when you check the fifth bit and it is 1, again you do not have any option here because there is no right child for this one. Okay, so in all the cases, now where will you go back? Your last best match prefix. That means in all of these cases, you will say that, okay, A is my best match prefix. But this is like not exactly true. I mean, not exactly the best match prefix. You are simply looking at the first bit and saying that, okay, this is the best match prefix. All right. So what we are trying to do, we are trying to make it a disjoint prefix binary try. So what we do, we put a right child here and we put a right child here too. Okay. But these are essentially overlapping with which prefix that already exists in your prefix set. It matches with 0 star, right? That means A. So it is a variation of A again. So you have like A1 and then you have like A2 and you have A3. Okay. So this is what your disjoint prefix binary try looks like. And similarly, when you get to this part also, you will find that in the binary try, this one was D, that is 1 star. And this guy never had a right child. So you have a right child here, so which is like D1 here. All right. So essentially, if you look at this try now, okay, if you look at this try now, you will find that no internal nodes are having any prefixes. Okay, all the prefixes are now pushed to the leaves of this particular try. Okay, so this kind of a try where the leaf nodes are basically where the internal nodes are pushed to the leaf nodes with the prefixes, this kind of a try is known as, or this technique of pushing those internal nodes to the leaf nodes is known as leaf pushing. Okay, so with this you are essentially having all of the prefixes in your leaf node. in your leaf node. So this is also for, this same set of prefix. If you further expand it, okay, if you further expand it for more and more number of prefix options that you can have, then this comes out as an expanded disjoint prefix binary trie. Okay, so you will see that, this is your A1, and then A1 will have so many, like, this is the variation that you are getting for A1, and for C you are getting these many variations. So this node is being pushed to these leaf nodes, this node is being pushed to these leaf nodes, this node is being pushed to these many leaf nodes. Okay, so like that you can further expand your disjoint prefix binary trie to bring everything at the same level. Okay, this one was not everything was at the same level, so if you want to put everything at the same level, so you can still further push them down, and then you can see that, okay, this is coming out like this. Okay, so this is your expanded disjoint prefix binary trie. Now the question is, how do I transform a given set of prefixes into a set of disjoint prefixes? Okay, so how do I transform it? We have already seen it, but just to formulate it properly, first you need to make a binary trie. Okay, whatever set of prefixes you are having, make a binary trie. Then find out all the nodes, internal nodes, which have only one child. Okay, for those internal nodes, you first add leaf nodes. Okay, now these leaf nodes will become your new prefixes that will inherit the forwarding information of the closest ancestors, which are your prefixes. Like we did it, like right, like A was 0 star. Okay, so whatever internal nodes were there which were not having any left or right child, so we were putting A1 A2 like that, okay, in our disjoint set prefix. So this is the part here, that is, if you have leaf when you have new leaf nodes, they will be given prefixes that inherit the forwarding information of the closest ancestor, which is marked as a prefix, and the internal nodes that are marked as prefixes are unmarked. So internal nodes are now unmarked. There are no internal nodes that are basically having any prefixes. All of them are now pushed down to the leaf nodes. Okay, so this is how your disjoint set prefix trie can be made. And of course, we have got to know this information, that this technique of pushing the internal node to the leaf node is known as leaf pushing. Okay, I hope that all of this is making sense, because I'm not getting any question in between. So I'm not sure whether it is actually making sense to all of you or not. I'll hope that you have questions after the end of the class. Okay. Otherwise, see, actually, I will show you what I'm actually looking at. This is the paper that I'm looking at. Okay. This is the one. Let me show you. Okay, so this is basically written by Sanchez, Biersack, and Dabos. Okay, so this is basically a survey and taxonomy of IP address lookup algorithms. This is the paper from which I've taken today's class. You will also get the information from Medhi and Ramasami's book, but I think this one will give you a better understanding. So like here, see, I'm giving the example also, same examples as they have given here, so that, when you look at this paper for better explanation, you will not have any problems. Okay, so see, here you have requirements on address lookup algorithms, then you have like binary trie. This is the example that I'm actually giving you in the class. Okay, so you have the binary trie here, then you have path compressed tries, This is the path compressed tries that I'm talking to you about. Okay, this is the path compressed try. And then you have new IP lookup algorithms. We have already talked about search on value approaches, search on length approaches. Then we got to talk about auxiliary techniques where we were looking at prefix transformation, and we started with disjoints at prefixes. So this is the disjoint prefix binary tree. This is the expanded disjoint prefix binary tree that we were talking about just now. Okay, so this one will be a good reference for you. So please go ahead and check this one. Okay, I will upload this also as a note for all of you. So this is the one. Now let me just get to multi-bit tries. This is here. Before that, let me. Achha. So first, we have talked about disjoint set prefixes, right? Like disjoint prefix binary try, where what we are doing, we're expanding the prefix. How it helps if we expand the prefix? You will get a better match than what you were getting earlier. That is how your expansion of prefixes helps. But if you expand your prefixes, one more problem is that you are actually going to keep a lot of more nodes, extra nodes, right? Which is also not very helpful for you. Okay, so here now basically what you are doing is you are trying to see that what will be the best kind of algorithm that I can use. So you try to find out the worst cases in all the scenarios, or the best cases in all this. I mean, the limitations, okay, the limits that you can get. Like I will try to have like maximum prefixes with me, and then I will try to find the best match so that I get the accurate best match, or most accurate best match, or approximate best match for my particular IP address. That is one way of approaching to the problem. Another way of approaching to the problem is that if I am doing too many prefixes, I have to check. That will be time consuming, so search complexity will increase, and also memory will I mean the memory consumed and access time, that will also increase. Okay, so I would compromise on finding the best match prefix, and I will reduce on these other aspects, that is reducing the memory that has been used, reducing the access time, reducing the search time. Okay, so we will try to see that in both the cases what can be done. Okay, what are the ways in which we can find out that okay, we compromise on something, we get some other aspects of it. Okay, so like that we are getting to the compression techniques here. Okay, so how does compression technique help? It helps to reduce redundancies from the encoding. Okay, so why is it done? Because as I told you that I want to reduce the amount of memory consumption. I want to reduce the time which is required to retrieve the best matching. Okay, so that means your search time should be reduced and you have a minimum number of memory accesses. Okay, so these are the motivations for having better compression techniques. Like just we saw, we compressed a binary try using path compression. Now, a few more points to note here. That is, first one is application of optimization techniques. Okay, so optimization basically allows to define some constraints, and we know that when we are talking from the point of prefixes, it will help you to find the right set of prefixes that satisfy the constraints that you are basically looking for. Okay, so what is the objective in our case? That we want to minimize the amount of memory consumed. Okay, now next part to consider is the memory hierarchy in computers. Okay, so as we all know that memory access is quite expensive. Okay, so what can we do? We can use small data structures, because they will make it more likely that your forwarding table fits into a faster cache memory. Okay, so that is one way. Another is that of course you need to reduce the number of memory accesses so that your search becomes much faster and less costlier. Okay, so these are the things that we need to consider as an objective while trying to find out a better algorithm for lookup. So now what we want to do. Okay, so until now what we saw that we can have disjoint prefixes where we are basically um, expanding the prefixes, and we are ensuring that we find the best matching prefix for our particular address that we are checking. Okay, so that is one way. Another is that that will increase redundancy, so we need to reduce the number of memory accesses, so somehow we need to use some kind of compression. Okay, so these are the two things, but these are the two extents, right? Two extents are there. Now we need to do a compromise. Okay, we need to come somewhere in between so that we will try to have this also and some part of the other also. Okay, so for that reason we come to the concept of multi-bit tries. Okay, so first let us see what are the features of binary tries. So what are the features? First is that it can handle prefixes of arbitrary length very easily. It can do, because you don't have to do anything as such. Simply you just keep adding the nodes as and when required, depending upon what is the prefix that you are having. Okay, so any arbitrary length prefix, you can simply do the insertion. Okay, and you can update also accordingly. But what will happen with this? Your search will become very slow because you are examining one bit at a time. Okay, every bit you are checking that will give which side, which particular noun node we need to traverse to. So that becomes time consuming. All right. So for this reason, we get to the concept of multi-bit try. What we do in multi-bit try, as the name suggests, we are taking a look at multiple bits. Okay, so you examine multiple bits at a time so that your number of memory accesses is reduced and your search is fastened. Okay, search speed is fastened. So how do we do that? So we have to first find out now that how many bits are we going to check at a time. You cannot just take some arbitrary number of bits and then check, because you might miss out some important internal node bits which will actually give a different different result from your forwarding table. Okay, so what is the first decision? You need to first find out the number of bits that you are going to check at each step, and that is known as a stride. Okay, that is the number of bits that are to be inspected per step. Okay, now stride can be either fixed size or it can be of variable size. Okay, so here is the definition for a multi-bit try. That is, a multi-bit try is a try structure that allows the inspection of bits in strides of several bits. Now strides can be either fixed stride or it can be variable stride. Now each node in the multi-bit try has 2 power k children, where k is the stride. Okay. Now if all the nodes at the same level have the same stride size, then it is called a fixed stride. Otherwise it is of course called as a variable stride, as I was telling you. So let me show you some more features of multi-bit tries. So first, what does it imply? It basically allows the data structure to be traversed in strides of several bits at a time. So that means your memory access and search time both are reduced. So the problem with this one will be what? In binary try, you could add an arbitrary length prefix. There was no problem with this. But here if you are having fixed stride, or if you are having a particular stride size, then it will be difficult to support prefixes of arbitrary lengths. So that is the problem that your multi-bit trie gives you. Now, if you have a multi-bit trie, okay, with some stride size, what you need to do? You must transform your prefix into an equivalent prefix of longer length to confirm the prefix length allowed by the structure. Okay. Now, let me go to this part. Okay, so this is your fixed stride multi-bit trie. Okay. Now, what is the stride size in the first level? The stride size is 3. So you check first 3 bits in the first level. Okay. Now, given the prefixes that you are having, you have A as 0 star. Okay. Now, what are the 3 options that you are having with, if it is if you are checking 3 bits, first 3 bits? So you will have 0, 0, 0, 0, 0, 1, 0, 1, 0 and 0, 1, 1. Okay. So these are the 4 options that you will have, starting with 0, which start with 0 and up to 3 bits. Okay. So essentially what you are doing here, look at this point that we were saying, a prefix must be transformed into an equivalent prefix of longer length to conform with the prefix lengths allowed by the structure. So that's what is happening here. 0, 0, 0 to 0, 1, 1, these are the different different variations of 0 star that you can have. Now, C is already there with you as a prefix, that is 0, 1, 1 star. So C will be here. But the rest are variations of A only, that is 0 star. So you put them as A here. So A and A here. Alright. Now similarly for this guy also, for like D. Okay, D was 1 star, but 1 has several variations, like with up to 3 bits if you go. So you will have again 4 variations. So E and D are already available with you. That is, sorry, E is already available with you. That is 100 star. For rest of it, you put them as D. Then again, further you go ahead with the stride size. Now in this one, the stride size is 2. So 0001. Here you have already this one, that is 0100 star, 01000 star. So you just, so this is 010 and then 00 star. So you get B here. Okay, and rest are not given here. These will be again variations of this one only, the previous node that you have. So the best matching prefix in those cases will still be 010, that is this guy here, the A. And then you have D and then the corresponding children here. Okay. So I have already extended the class time today by 2 minutes anyways. So I hope that this part is clear to you. Please go ahead with this one once again. Go through the lecture of today once again. So that you have a clear understanding. I hope that you have understood, or if you have any questions you can ask me.